I'm Doug Sweetser, owner of Quaternions.com, the guy in the black hat. This is a talk I gave to the APS meeting in Boston. Big thing, like 5,000 physicists in town. And the title is Quaternion Series Quantum Mechanics, putting on some positive spin. Why do I have to put on positive spin? Well, in a very brief exchange I had with this famous physicist, Scott Aronson, who's very into quantum information theory and practice, he got an appraisal of the idea and said, gee, that's not too interesting because, if it's really so similar to complex quantum mechanics, then, why bother? Well, hopefully I'll give you some reasons. We'll see. Okay, so there is a lot of negative PR out there about quaternions. And it started back in the day. Lord Kelvin. That's when you're being slapped around. The Lord is actually putting it down. And I love that he called it an unmixed evil for those who've touched them in any way, including James Maxwell, clerk of Maxwell. And it's like, Maxwell was amazing. You're slapping him down too? All right. But the sport continues. In 86, this guy, Simon Altman, said, Quaternions appear to exude an air of 18th century decay. No hard-headed physical scientists are going to get near this sort of thing. And it's like, sorry, you might think I'm a zealot. So no, I am like a cold-blooded rationalist. It's like, what can you do? What can you not do? If you can't do something, give it up. And that's it. That's the bottom line. Be a hard-headed physical scientist about it and don't get too passionate. But the passions are still there. Scott Aronson said in 2018, December, he said, it's a flaming garbage fire if you try and use this stuff to do quantum mechanics. Like, well, why did he have such a strong opinion? It was based on a calculation he did. All right, so why, if you go to the literature, do you say, I shouldn't bother? Okay, you can't derive the Maxwell equations. You need these biquaternions, and then it's doable. You can't do the Lorentz transformation sort of thing using real value quaternions. You need biquaternions. General relativity, no go. Unless you're into this guy, Mendel Sachs, who I don't think really got caught on or got much of a school going. And the calculation that Scott Aronson did was about superluminal transformation of information. And if that's the case, give it up. Well, if you go to Quaternions.com, hey, we're addressing these issues. And I say addressing because I don't live in this illusion that I'm so good that, like, I say it and it's right. No, I'm an amateur. I'm going to make misstatements, and I'm going to be kind of present things in a way that's not professional, and is always going to be like that because I'm never going to be a professional. So there's always going to be rough edges to my work. I just want to put that out there at the start. All right, so EM, you do this particular calculation and you get this b squared minus e squared term, which is Lorentz invariant, and that's standard theory. You put that into Euler-Lagrange machinery, and out comes the Gauss's equation and Ampere's law. So that's pretty good. And those are all real valued. And you also get the Poynting vector, which to me is a good thing because that cares about which direction time goes in. It actually flips signs, unlike b squared minus c squared. All right. The Lorentz transformation, two guys, Silberstein and Conway, I believe, 1910, 1911, said, well, let's fire this engine up and do a Lorentz transformation this way. And they did it just like you do a rotation, a triple product. And it totally doesn't work unless you use biquaternions, and that's what they publish on. And I'm like, well, why don't we just try a little harder, people? And so if you just use a couple other triple products, then you can actually get the kind of totally standard result. And this is, as far as I know, it's not published or out there, but it's done. It can be done. All right. Then gravity. Well, I don't think about it in terms of general relativity. I have a much more radical idea. I'm not sure if you can see this t-shirt. That's it. This is kind of a 45-degree rotation of this, the light cone of special relativity. And I'm going to actually do a poster session on it, see how that goes. All right, and then finally, there's this thing called this CHSH inequality. 4 names, forget them. And it's a generalization of the Bell's inequality. And I showed how to do it with complex values, which is totally boring because that's what everybody does. And it's relatively easy to go from that proof to the one that's more general, more quaternionic. And I've got a IPython notebook up on GitHub that shows 70% of the time how to do it with the complex values, and the last 30 is, it applies to the quaternion case. And of course, that only works if you're respecting the speed limit. If you actually go to Scott Aronson's post on, why are amplitudes complex, you can see the problem. The problem is that the operator he decides to analyze has a trace that is complex valued, and that means it's not an observable, and therefore I don't care about his analysis. Now, he got that actually from a paper on a preprint server, and I did write the guy who wrote that preprint. He hasn't gotten back to me because I'm just a guy in a basement. So, but you can look at it and you'll pick it out immediately and know it has no there's no weight. It can't have any weight because it's not an observable, and that's the way it goes. All right. So what we're going to do is go from complex quantum mechanics to Quaternion Series quantum mechanics. Now, I do write my complex numbers oddly because I don't know, I like being odd. You get a different angle on things. So the real number, I don't just write it as t. I write it as t times x to the 0. Well, x to the 0 is just 1. So that's a real value, plus x to the I to the 1, and that's imaginary numbers. So together they make up a complex number. And I do put an I in front of both because to show that they really have an intimate relationship, which sometimes you miss out on that when you're brought up traditionally that here are the reals, here are the imaginaries, and somehow they don't mix it up, and I think they definitely do. So to make it a quaternion, 4 parts, you need 2 other imaginaries, a j and a k, and you just add zeros. So that's really pretty easy. But, you could make the j be the non-zero guy, or you could make the k, or you could make them all have values as long as you normalize correctly. Now, I think the normal reaction to that is what Scott Aronson's reaction was, which is that's boring. Because you're writing the same thing in a bunch of different ways, and I couldn't be more bored. Except that boring means you're dealing with a symmetry, and symmetries are the engine of modern physics. So what I'm saying is you take this inner product of a wave with its conjugate, and now we're going to shift around that wave function a little bit. And how can we shift it around if it's a Quaternion series? Well, you could point it in a different direction. And there are at least 3 different ways to do that. One is to use the group U1, which is also known as the unit complex numbers. So phi will be pointing in a direction, and U1 will point in exactly that same direction, but it'll be, when you form the product, it'll shift things around a little bit. What happens with the group SU2, which is actually known as the unit Quaternions, is you get a little bit more freedom about where the heck this thing ends up pointing. And that's fine, but it isn't going to change the size of that at all. And then finally, there's this group Q8, and that's easy to describe. You could have +1 or -1 times that phi, or you could have plus I or minus I, or plus J minus J, plus K minus K. It won't change the inner product like at all. Now that is not SU3, but as I only vaguely know the history, there were two qualities that they needed out of SU3. One was it had to have 8 elements, which is what 3 squared minus 1 is, the S being the -1 part. And each of the generators had to have a normal 1. Well, those two qualities are actually covered by the group Q8. So that's kind of nice. But I literally don't know how to do a single calculation with a weak force or with a strong force. So I certainly don't know how to formalize a possible link to the standard model from these observations. What I do know is that I've done absolutely nothing other than say I want to form an inner product, and I've got 2 out of the 3 symmetries like exactly that appear in the standard model, not sometimes, but every single time I say I've taken an inner product. Those are there, and that's like scary amazing to me anyway. And then I've got something that's got 8-fold symmetry. The 8-fold way perhaps in a different way. Wild stuff, but it's like built in there without adding it. Because if you say, how does it done in the standard model? It's like, well, I want to add this thing in, and I got to add this thing in. Oh, and I got to have some internal symmetry stuff. It's really hacky. This doesn't feel hacky. This feels like the way it is, because that's the way nature is. All right, so boring could in fact be amazing. I'm not going to be able to bring it to the market, but I hope that's not a mirage I'm looking at. Okay, so here is another big idea about why doing things with quaternions is so valuable. Because physics should be physical. Now, when somebody says, I'm using complex numbers, I'm going, I don't have any idea what you're doing, really, okay? When I say I'm working with quaternions, it says to me that I've got a real part and I've got 3 dimensions of space. And it's like a finger snap. That to me is what a quaternion is. Finger snaps, events that have specific times, specific X, Y, and Z. All right, so if you have a wave function that's a collection of time-like events, then you can always calculate its conjugate. And you just put a bunch of minus signs in there. Oh, and I've got a visualization of that. If this is X, Y, and Z, and this is its mirror image, all you have to do is rotate it by 90 degrees, and up is down, near is far, and left is right. So that's good. But the important thing is that all the events in your wave function, are space-like separated from those in your conjugate. That's why quantum mechanics has all this non-locality that no matter how clever you are, you cannot get rid of it in any way. And to me, that's pretty cool. All right. Okay, so I have to work with quaternions that basically pretty much commute most of the time. Not all the time, most of the time. And when I was thinking about that, it's like, that sounds unreasonable. If I take 2 quaternions out of a hat, they're not going to commute. But then it was like, well, what are experimentalists doing? Are they just looking at any old place? Do they point like a drunk? No, wherever my experiment? No. physicists do drink, but they don't drink and do experiments that get published. No, they point with extreme precision. The most famous ones probably is not a quantum experiment. It's the one LIGO, where they care about the vibrating of that mirror to such an extent that you don't have to worry about, say, the semi going by or the beach sort of thing. But physicists, will look at incredibly small volumes of space, like with super cold atoms, these places where atoms are jumping around, and they'll focus on such an incredibly amazingly small space. This is a picture from somebody's light table, but you've seen lots of these light tables, and they're always focusing amazingly on one incredibly small place. Now, if that's what experimentalists are doing, then I think your math tools should do the same. So if I say, well, all my quaternions point in the same direction, you shouldn't have an issue, because that's the way experimentalists do it. Yeah, but do we have any example of that? And it's like, yeah, we got a huge body of data like that. And that is that if we take all the equations done in quantum mechanics since the 20s to today, well, that's a large set. And they all point in one direction, and that is 1i, 0k, 0j. And all I'm saying is, spice it up a little. I mean, feel like you can spice it up a little. All right. I did say this talk was going to deal somewhat with Pauli matrices, and mostly people talk about the relationships between sigma x, sigma y, and sigma z, but I don't see many people talking about what those things actually do. And so if I've got a two-state system, T1, x1i, and T2, x2i, what sigma x is going to do is just flip the ones for the twos, okay? And what the z is going to do is it's going to just do -1 times that second state. It's sigma y that really messes things up, okay? Because it switches rows, twos for ones, and then reals for complex. Now, when you start combining these, it basically scrambles the information between the two in all kinds of different ways. And that, to me, is what the Pauli matrices are doing. Now, with my set of tools, each one of those is actually 4 quaternions. Sigma x is a 0 quaternion, a 1 quaternion, a 1 quaternion, and a 0 quaternion. And it's an operator, so it's got 2 rows and 2 columns. And so I don't look at sigma x and think it's just a quaternion. I actually see it as 4. That's the way my formalism works. Okay, so I want to be clear about the difference between a quaternion and a quaternion series. Okay, so quaternions are is a norm division algebra. So that means if you take the product and then the norm, it's the same as multiplying the norms of each one separately. And it's a division algebra, so that means that the additive identity, there's only one, and there's only one multiplicative identity. Whereas quaternion series has orthogonal vectors. So A and B are not negative, but if you take that inner product, you can get 0 if they're orthogonal. And it's also a semigroup. That means there's just like this one additive 0, and then there are 2 to the n multiplicative identities, depending on what you're kind of dealing with. All right? So what I'm hoping to show eventually is that the quaternion series is rich enough, particularly if you use these ones that point in one direction, that it could be the algebra of quantum mechanics. And the research will continue. I've got a GitHub project devoted to this particular book by Susskind and Freeman on quantum mechanics. I've got these IPython notebooks. It's not an easy read, okay? It's just seeing if I can figure all these things out. It often takes me months or longer to get through a chapter. It's not easy work for me. I've done 3 out of 10 chapters. I've got to get 10 out of 10 chapters. It's just that simple. If I don't, then the proposal is wrong. All right. So this talk is up on the web, and you can reach me at quaternions.com. It should be easy to find my email address. All right. Thank you very much. So how'd that presentation go? Well, it was pretty standard. There were like 30 to 40 people in the room at the time. And since there were 15 presenters and maybe a few of them had their friends, a few stragglers, it's basically a talk to other people who are giving talks. And each of those people comes with their own collection of jargon. And it means that the amount of communication between anybody is really pretty rare. Now, if you have a couple of talks and they're all from the same lab, those people understand each other really well. And there is some feedback between those people. But if you're not in their lab, there's really hard to understand other folks. And that means other people didn't understand me either. And that's because at least half the people have never heard of the word Quaternion before. So you have to explain that. Well, right there, you're not going to win them over. You come up with like this thing that like no one's heard of before. And even if they have heard of Quaternions, they know it's good for a thing or two, and that's it. And they're going to leave thinking the same thing, because you can't really force them to engage and get wrapped up in it. And that's okay. That's what happens. So it cost me about $600 to go there. It was like a 4-day event. Was it worth it? Absolutely. Because I got this wonderful slide out of it, actually. The one that's got the wave function on one side is conjugate, space-like separated from the wave function, which means that non-locality has a nice, clear explanation. And then you've got the observer right in the middle, sitting at 0, 0, 0 in space. And that, to me, that one slide it made it all worthwhile. All right. Thank you very much.